Hey everybody, welcome to our last talk of the day. This should be a really good one. We have Leonahenahe Basque here, PhD candidate at the Arizona State University, and he is going to be giving a presentation about binary hacking with LLMs. So thank you all so much for coming here, and I am going to turn it over to him.
Thank you. Awesome. Thank you so much for the introduction. It is a pleasure to close out day one and start the snowstorm. So I hope you guys are ready for a fun talk about this kind of research space of decompilers, of binary analysis, and generally how you use AI in the mix. So let's kind of get into it. We have 20 minutes, so it's going to be kind of a crazy speed run on this topic space. But just to waste time in the beginning, let's talk about me. So who am I? Who is this guy? I am a final year PhD student at Arizona State University. I am currently on the academic job market. You know who you are. I research things in how to make programs more understandable, how to make them more fixable, how to make them more secure. To do so, I do a lot of different research in different areas. I do in the area of decompilation, which you might have seen a previous talk about. I do it in AI for security, which is highly related to AICC, if you're familiar with it, or generally reverse engineering. How do hackers go about understanding programs and then doing the cool things we love doing with them? To do so, I participate in this big team called Shellfish. We do a lot of hacking and CTFs, and I'm in this research lab called CEFCON. So now on to the actual content, right? Can LLMs hack? I am sure many of you have already asked this question. People are yapping about it a lot, that LLMs are hacking everything, they're breaking everything. And the kind of big question that I want to bring to this talk, right, is like, why even talk about LLMs in security at all? And how is it relevant to binaries? So let's talk about the relevance to programs, right? Nowadays, programs are just too big. Fundamentally, they are getting bigger than ever. LLMs are helping them get bigger than ever. The average size, right, of a normal open source project is more than 100,000 lines of code. You have Nginx, you have SQLite, you have libxml. All of these programs are pretty dang big. And to kind of scope it to how big it is, let's talk about what we think of the holy jewel of security, and that would be symbolic execution. Symbolic execution, is the fun, like cool academic-y type of thing. You solve constraints, you can prove if something is safe or not. And generally, it scales to about hundreds of lines of code. Like if you're lucky, you can get it up to 1,000 maybe, and that's really stretching it. While LLMs, on the other hand, really kind of blow this out of the water. They scale to an order of magnitude of 2 times bigger, right? So we're at 10,000 lines of code. We are stretching it to the max of whatever the context window is. And if the past is kind of telling of the future, this will only get bigger. But a valid question you might be asking is, okay, cool, they can scale to lots of lines of code. We all know that. They can read a lot. But are they actually effective at this job of reading code and doing things with it, like finding 0 days? Well, over the last 2 years, DARPA has aimed to answer that question, if LLMs actually can find 0 days and fix them autonomously. The 2-year program called AICC, where they basically gathered all these scientists, all these businesses, and said, go solve this problem, use LLMs to hack, and tell us how it goes. And if you do it, you get a lot of money if you win, right? So that was kind of the big selling point. Together, these teams came with their different things called cyber reasoning systems, which have the aim of doing this kind of straightforward process. You take in a big open source project, it goes in, it gets crunched by the LLM, you do some fancy security things in the middle, and out comes a patch and a 0 day, right? So kind of straightforward what it does, but how you actually get there, rather complicated. Now, you might be asking, did these cyber reasoning systems do anything impactful aside from play a big game by DARPA? And in fact, they did. Aside from the projects these teams got to see, including our own, we built our own cyber reasoning system, there were actually a bunch of projects that we never got to see. Things that our system was ran on completely offline, and we had no idea it would be ran on it. So of those systems, almost every single system took in a project that was more than 100,000 lines of code on average. These were massive open source projects that were being crunched on and finding things on. And then these cyber reasoning systems found around 18 0 days across all of them. I don't want to sleep on this number. 18 might sound like a small number, but consider the fact that these systems had never seen this source code before. These are essentially free 0 days. And when I say free, I mean pretty dang close. On average, these 0 days cost 152 LLM dollars, right? So spending on your API credit. That's kind of a scary number, right? These open source systems are available to everybody. You could run them right now on anything and potentially find a 0 day for $150. These were projects we didn't test on and it just worked, right? So I would say that in 2026, we are entering a new age of LLM-driven hacking, and it's serious, it's real. There are real results, and you can get real bugs out of it. Now, you might be thinking, okay, I've used an LLM before, and if LLMs are as crazy as you say they are, why isn't the world just going nuts, right? Why isn't every single script kiddie kind of coming out of the woodwork with a 0 day in Linux kernel? And that's because making them work very well actually takes a lot of expertise, right? You do a lot of validation between the input and the output. LLMs are not this magic machine that just takes in garbage and outputs treasure, right? You have to do a lot of validation in the middle. So studying these cyber reasoning systems and what all of them did is kind of a similar model, right? You have the source code, you do all these formal analyses in the middle before actually getting to the large language model, and then you validate the output. I really want to tap down on that first part, the input. How do you validate the input? Well, most of these were really good source code. They were nice source code made by great project developers, and the formal analyses you could do on it was pretty sophisticated. But what happens when you take away the source code, which is, of course, the topic of today's talk? What happens when you want to do cyber reasoning systems on systems that only have binaries, like a drone, like an autonomous car, like a medical device, where you're not going to get the source code? Well, naively, you might say, okay, well, let's take this thing, let's extract the binary. The binary, we'll give it to the LLM like we've done everything else. The LLM says, no, I don't like that, right? It doesn't want to see a bunch of unstructured data. It doesn't want to see assembly. It wants to see something it was trained on, which is largely source code. So you say, okay, well, I know how to get source code out of a binary. You give it to a decompiler, and you're like, okay, decompiler, give him the source code, and then we're going to do some stuff, and we're going to find some bugs. Sounds pretty good. No source, no problem, right? We put in the binary, it goes through the decompiler, chugs away, and then boom, we get some bugs. Unfortunately, that is not what's going to happen. You're actually going to get a bunch of garbage. And that's because decompilers don't really make source code. This is, the big hidden thing. They don't actually output source code. And in fact, they don't even get close to outputting source code, which is kind of the whole point of why they're so bad here. Let's do a little example. I won't go too far into it because I've kind of done this in previous talks before, which you can check out at that link below. But when you generally have source code like this, a few lines, you compile up that source code, you go to decompile it, and all of a sudden it looks like this. It gets exploded. This is what you might see in your $8,000 or $10,000 a year decompiler, no names, right? You decompile it, it looks like this. There are calls everywhere that don't look like the source code, right? There are actually 3 calls in the decompilation and only 2 in the source code. There's also these go-tos everywhere. The if statements have been moved around. Generally speaking, decompilers are not giving you the source code that you want it to give you. And that's actually very important for large language models, which are not humans. Remember this. So, does this really matter? All right, I'm showing you bad decompilation, and we all know decompilers are bad, right? They suck. So a case study then of what really happens when you have bad quality decompilation. So here's the case study. We take Nginx, one of the big targets from AICC. We compile it up. We get a binary. We strip that binary, so it's just like any binary you would find out in the wild. We leave the function names, though. And then we give it to 2 different decompilers, the Anger decompiler. You can swap it in for IDA if you like. And then the Ghidra decompiler. We take both of these. We take, the CRS you might have on hand, which would be artificial, RCRS, so take the CRS. You take that CRS, you give it these 2 decompilations, and you say patch the bugs. Find the bugs, patch the bugs. And it should generate you patches, right? So here is the case study on one example. Here's Nginx. So this is one of the vulnerable functions at AICC. They put some error in here to make it a little buggy. This is the Nginx send file. There's a bunch of lines here. You can kind of just glaze at the structure and do what you want with it with your eyes. But there's only 2 lines that really quite matter. In the prototype, there is a size. You are sending files after all, and these files have sizes. And then you want to allocate that into memory so that you can mess with it. There is a bug here that in the allocation, it is a constant allocation for a size which is, of course, dynamic. You could be sending a file of any size. So it's usually allocating 100 bytes, and you can, of course, always have something bigger than 100 bytes. So that's the AICC bug. You're allocating a constant size for a dynamically large input. The patch is rather straightforward. take that allocator and just put the argument all the way at the top in the prototype, the size. You just allocate exactly for the size of whatever's coming in. Pretty straightforward. So the patcher doesn't get the source code, it gets the decompilation. The decompilation looks like this. Here's anger, looks kind of meh, kind of okay, right? There's a bunch of OXFFFs everywhere, it looks kind of a little gnarly, but the important stuff is there. The Nginx alloc is there, which has this, allocator of a constant size, and we see A2, which of course doesn't have a name, but that is the size. We also have Ghidra, which is similar in badness, right? You have the OXFFs everywhere. The if statements are there. They're a little more like indented and scoped in this time, but generally speaking, if I was human, I'd look at both of these and be like, about the same bad. The names are like a little worse in Ghidra, but I don't know. It's not fundamentally worse, right? So we take these and we say, all right, go ahead, patch them. Here's a crash. Patch on that function. So you take anger, you give it to an LLM, and it generates a root cause. It says there is a dynamic, there is a heap buffer overflow here. You give the Ghidra one, and it works the same. You also have a heap buffer overflow. Great. These two large language models independently have come to the same conclusion on different decompilations. Everything looks great. So you take that reasoning, anger, decompilation, the reasoning, and all of a sudden it produces the correct patch. Sick, we're doing binary patching on decompilation. But you give the Ghidra one, and you get a crazy patch, and this is after 5 attempts. So this is kind of weird, right? Like, they had the same reasoning in the middle, but you gave them different decompilations, and somehow they've created completely different patches. This looks really bad, but it gets a little bit worse. Look a little closer into this patch. So the patch was supposed to do like a dynamic size. It was supposed to use size parameter. But instead, what it actually uses, it says, actually, let's just make it much bigger. So it goes to 100,000 and allocates that. This is a terrible patch, but it actually gets rid of the POC. Like the POC we had for this, the one we generated, it was only like 10, I think it was 1,000 bytes, right? So it'll get rid of it. So this is actually really bad because if you had this in a real scenario, it got rid of the bug and introduced a new bug, which is much worse, right? So this is bad. This is security critical. But why does it fail, right? Understanding why it fails is kind of the important part of the talk. Is this just magic? Is this just like LLM stuff, non-determinism, it's just crazy? Well, no, there is a little bit of explainability here of what's going on. Between the two decompilation, there is the only major difference is in the structure of the code, the control flow structure. You can kind of just like glance at it and see where the if statements are. On the left-hand side, the anger decompilation is actually quite linear. If statements happen, you stay in one scope at a time. On the right-hand side, you can go 3 scopes deep. They are structurally different. Well, how structurally different? We can actually measure this automatically. We found an algorithm to do it in 2024, and now we can do it automatically. So what we do is, you take 2 codes, you have 2 random codes you've pulled out of your pocket, and now you create a control flow graph. So you go and grab an undergrad student, and he manually makes the control flow graph on a piece of paper. And then you scan that, and you put it here. But anyway, you get a control flow graph for these 2 source codes, right? And what you're really asking is, given the left code, how do I turn it into the right code? So you're saying, how do I turn the left graph into the right graph, right? So what you would actually do is edit the graph. So you delete these 3 edits, this one edit, one edit, one edit. You delete the 3 ones there, boom. Now you just have these floating nodes. You get to delete those for free, and boom, it takes 3 graph edits. So we would say that the first graph is a graph edit distance of 3. Traditionally, this algorithm is NP hard, but we created an approximation algorithm to do it a little faster. So it is a 3 graph edit distance between these 2 graphs. A rule of thumb for this is that anytime you see 3 edits, that's about 1 if statement. So if you see 6 edits, it's like deleting a whole if statement and adding it back. Between the Ghidra decompilation and the actual source code, it is 6 graph edits. So it takes you 6 edits to turn the left one into the right one. And that's actually rather important because 6 edits caused a failure. Anger, on the other hand, was structurally correct exactly on this one. 0 edits to source code, and that got you the exact patch. So somehow, between just a matter of moving an if statement twice, we have a drastically different outcome. But does it scale to more than just this example? Well, here's a few more of these patches in Nginx. So we take Nginx, all 14 AICC bugs. We take more decompilers. We bring IDAPRO into the mix because it is, of course, the industry standard. Ghidra and Anger. No binary ninja, keep yourself quiet. And 3 trials. We do 3 trials on each one so that we have a little bit more, sciencey stuff. So this is the sad fact. The overall success rate is a sad 15%. So if you try to do a patch with decompilation on the same AICC data set, you get a 15% success rate, which is rather sad, because in the actual competition for Nginx, teams were hitting around 90 percentile, right? Almost 100 all the time. This is also sad for the unique patches that get developed, that come out of this when you do it on decompilation. There's only 5 out of all 14 patches possible. And in AICC, most teams, including ourselves, got 14 out of 14. So when you lose source code, you go to decompilation, you just kind of automatically get a 50% cut. But there's a little bit more nuance into how the cut happens. Of all those 126 patches in that new data set, right, of the 14 AICC bugs, successful patches happened when the decompilation provided to the LLM was 3 edits or less on average, where the ones that failed were 12 edits or more on average. So what does this kind of mean? It indicates that the graph edit distance is actually indicating how useful your decompilation will be to a large language model in some task. For this one, it's patching. We, of course, can look at that per decompiler, and we see a very similar result. Here's all the ones we tried, which is Anger, IDA, and Ghidra. You have the first 2 at the top, which are relatively close. I'd say between 9 and 8, no one is better than the other. It could be up to error. It's very close, right? But Ghidra is kind of the odd one out here. What's going on? This is the average graph edit distance that these will produce at any time on the Nginx dataset. So not the patches only, but any kind of function in Nginx. This is the average graph edit distance it will produce. 10 edits for Anger, 8 edits for IDA, and 14 for Ghidra. Again, around 4 edit difference is now causing quite a dispersed, like a very different result in patchability. I think the thing I want to nail down here is that these large language models are not human experts. They do not behave like you think they will when even small changes happen. Moving an if statement once shouldn't confuse a human, but it will confuse a large language model. So what do the numbers mean? Well, the numbers mean when you get closer to source code with your decompiler, you often get better LLM performance, and that is in a multitude of tasks, right? You can start with patching, but this can also transfer over to pocking. So, all right, we kind of have this general idea that we want all of our decompilers to be closer to source code, and that will get us some better LLM stuff. But you might ask, all right, I think IDA Pro is pretty dang good, right? Like how much more do we have to go? And unfortunately, we have quite a large way to go. We have 22 edits is the average graph edit distance a decompiler will produce at random. So we take a bigger data set, we take 26 benign Debian packages, so that's about 8,000 function pairs, and we do this graph edit distance for all the decompilers and their output and source code. And we find on average even the best ones, so that would be between IDA Pro and Anger, are producing 22 edits on average. 22 edits, right? That's like at least 5 movements of if statements. That is the construction of loops. That's the destruction of go-tos everywhere, right? This is actually quite a bit of edits for what we are averagely at. And year after year, these numbers actually don't change that much, which is unfortunate because the community isn't prioritizing making these go lower, which I know we can do. Just because they haven't changed that much this year doesn't mean it's not possible. For instance, in 2022, Anger had a graph edit distance of 45 edits on average, which is obscene. It's crazy. That's a crazy amount of edits. It's a terrible decompiler. Of course, you didn't use it because it was a terrible decompiler, so don't use the 2022 edition. But in 2 years of research, we are able to bring it down to 22.64 edits, which is on average with what IDA Decompiler is doing for graph edit distance, except we don't have 30 years of decompiler experience, right? We're not decompiler devs all the time. This is what a bunch of PhD students and crazy professors make as a decompiler. So it is possible. We actually can do better. And I think that is the main thing I want to take away from this talk for you all, is that there are 2 main things. Decompilers need to be better for large language models. And secondly, we can do much better with decompilation in general. We can get to 0. 0 is possible. It doesn't have to be 22 edits. It just requires more focus, more research. All the other areas are still very relevant to doing LLM patching, such as byte match decompilation, such as delinking decompilation. These things are all very much possible. It will just take more research and more time and more community effort. But hopefully, with the open source stuff we do, we hope more people are willing to work on it and do more research. So the kind of outcomes of this talk, like what can you actually do with this information? What is actually relevant to you in your everyday life? Well, there's a few things. The first one, of course, you can try out our decompiler. Anger Decompiler is open source. It is hackable. It's Python. You can vibe code on it if you want to do vibe coding, whatever you want to do. You can use different decompilers, and statistically speaking, if you're to use decompilers in a large language model context, right, you should have at least a few of them, because during runtime, you don't know what your graph edit distance is going to be. So you should try to minimize for those that prioritize source code likeness. So it means just use many decompilers. Second one, you can fix the decompilation. The decompilation doesn't have to be broken forever. You could do deep research like we're trying to do. You can join us in collaboration, or you can even just do little edits. Like human edits really matter. You can do large language model edits. You can do all these types. And the third one, of course, you can hound the decompiler dev. You know who you are. You're in the room. Fix your decompilers, man. We can make it more close to source code, right? There are decompiler devs everywhere. Maybe you're paying for it. Maybe you know one. Hound them. Graph edit distance is something we can use to prioritize how good large language models will do in the future. It should be at form a priority of binary analysis for the next 5 to 10 years. How will we make the underlying source code for them more available? And with that, I thank you so much for your attendance, for your looking at this talk, for enjoying it. And if you have any questions, I'm happy to answer. Here's all the open source things.